Imagine the government hires you, and your entire job is to figure out if a 20-week publicly funded computer job training program actually boosts workers' hourly wages.
Or imagine you're working for an investment bank, right? And you are trying to prove if short-term U.S. Treasury bill strategies actually follow the economic theories they are supposed to.
Yeah, exactly. How do you even begin to answer these questions? Because, usually when we talk about a diagnosis, whether it's medical or engineering or whatever, there is this expectation of precision.
Right, you want a clear answer.
Exactly. You break your arm, the x-ray shows a jagged white line, and the doctor just points and says, well, there it is.
I mean, that's the dream, right? A perfect diagnostic tool.
But you step into the world of human behavior, of economics and public policy, and suddenly that x-ray machine is fundamentally broken. We expect data to be an x-ray, but in economics, we are looking at a diagnostic landscape that is entirely murky.
It is the absolute definition of diagnostic muddy waters. I mean, the variables are hopelessly tangled, the patients are, lying to you, and the machine itself might be altering the result just by being plugged in.
Which is exactly why we are pulling apart Chapter 1 of Jeffrey Wooldridge's textbook, Introduction à la Econometria, the fourth edition.
Yeah, and we are looking at this specifically to figure out how to fix that broken X-ray machine.
Right, because this isn't just about memorizing Greek letters or, blindly running software. This deep dive is about the architectural logic of truth in the social sciences.
It really is. It's the critical thinking toolkit you need for extracting reality from a chaotic, non-experimental world.
So that the next time you hear a confident headline claiming like policy X causes outcome Y, you know exactly how to pull that claim apart.
It is a totally necessary toolkit because knowledge construction in the social sciences is, well, it's fundamentally different from the hard sciences.
Yeah, the text makes a very firm distinction right at the beginning about this, right? It says econometrics is now an entirely independent discipline from mathematical statistics.
Exactly.
Okay, let's unpack that right away. Because if it's all just math and probabilities, why the schism? Why did econometricians have to pack up their bags and leave the mathematical statistics department?
Well, it comes down to the nature of the data. Mathematical statistics was largely built around the controlled experiment.
Okay.
So think of a natural scientist, right? Like a chemist or an agricultural researcher. If they want to know what happens when you mix chemical A with chemical B, they just go into a laboratory.
Right. They put on the goggles and mix the beakers.
Exactly. They control the temperature, they control the humidity, they measure the exact microscopic amounts, and they observe the reaction. They totally isolate the variables. That is experimental data.
But economists can't really do that, can they?
No, not at all. Economists, by and large, are what the text calls passive collectors of data.
Passive collectors.
Right, because we are dealing with non-experimental data. I think the text also calls this retrospective or observational data.
Yeah, it's looking backward at what already happened.
So if mathematical statisticians working in the natural sciences are like chemists mixing things in a controlled, sterile lab, econometricians are more like astronomers.
Astronomers, I like that.
Yeah, trying to figure out the fundamental laws of the universe just by staring up at the night sky.
I really like that analogy, but we have to push it further to really understand the handicap the econometrician is working with here.
Oh, really? How so?
Well, an astronomer stares at the night sky, yes, and they cannot move a star or pause a galaxy's rotation to see what happens. But an astronomer is observing physical bodies that obey strict, unthinking laws of physics.
Oh, I see where you're going with this.
Right. An econometrician is observing the night sky of human behavior. The stars in our sky have preferences, they change their minds, they react to being observed, and they actively choose their own paths based on this invisible internal logic. Wow. And we can't just force them into a lab to test that logic.
Exactly. In the social sciences, it is often impossible or prohibitively expensive or just morally entirely unacceptable to conduct the kind of controlled experiments you would need to get clean mathematical statistics.
Yeah, you can't exactly randomize people's lives for a study.
No, you cannot randomly assign one group of children to receive a terrible education and another group to receive a brilliant one just to measure the pure isolated effect on their future income.
The ethics board is going to shut you down before you even finish typing the proposal.
As they should. So economists are left observing data that has already happened. Data generated by people just living their lives, making complex, entangled choices in massive markets.
And because econometricians are stuck with this incredibly messy, non-experimental data, The standard tools of mathematical statistics just simply broke down.
They completely broke down. They had to invent entirely new techniques, like a whole new mathematical architecture, to deal with the sheer complexity and the hidden variables of economic data.
And the text makes it clear this isn't just an academic exercise for ivory tower economists. The applications are incredibly broad.
Oh, absolutely.
Yes, it's used for macroeconomic forecasting, like predicting the gross domestic product or guessing next quarter's inflation rate. But it goes way beyond the business news.
Way beyond. Econometrics is used to figure out how political campaign spending actually affects voting outcomes.
Wow.
Yeah. It's used to determine if a specific public school funding initiative directly impacts student test scores.
So it's basically the operating system for a modern policy evaluation.
That is exactly what it is. Anytime you want to test a theory, evaluate a government intervention, or make a complex business decision based on historical data, you are fundamentally relying on econometric methods.
Because without it, you are just looking at raw numbers and making wild, unscientific guesses.
Exactly. You're just guessing.
So how do we actually build one of these models? If we can't run an experiment, how do we construct a mathematical lens to look at this messy data?
Well, the text outlines the steps of an empirical economic analysis, and it says everything starts with formulating a question.
Which, I mean, sounds incredibly obvious.
It does sound obvious, but you would be surprised how often analyses fail at this very first step. You have to know precisely what you are trying to measure.
Like, are you testing a broad economic theory, or are you trying to evaluate a highly specific local government policy?
Right. The question dictates the entire architecture of the model.
Okay, so once you have the question, the text says you construct an economic model. This is where we start turning human behavior into math.
Yeah.
And the bedrock premise that underpins these models is utility maximization.
Utility maximization. It's the idea that people, when faced with limited resources, whether that is money, time, or energy, they will choose whatever option maximizes their well-being.
It's a powerful engine for these models, isn't it? Even if it is sometimes a bit controversial.
It is powerful, yes. It assumes a structured level of rationality. It doesn't mean people are perfect calculators, of course, but it means their behavior has a predictable direction.
Right. Like, if the price of a good goes up, utility maximization allows us to build a mathematical demand equation that predicts people will generally consume less of it.
Because it now costs more of their limited resources to achieve the same satisfaction.
But the text doesn't just apply this to buying apples and oranges. This is where we get into example 1.1, and I want to spend some real time on this because it illustrates exactly how economists translate the chaos of human life into a strict equation.
Ah, yes, the Becker model.
Exactly. It's Gary Becker's 1968 model of criminal behavior. Becker essentially said, let's stop looking at crime as just a sociological or psychological phenomenon, and let's treat the decision to commit a crime exactly like a decision to allocate resources in a market.
It was a revolutionary way to look at the world, and it literally won him a Nobel Prize.
Really, a Nobel Prize just for that.
Yes. Becker postulated that engaging in illegal activity is a utility-maximizing choice. A person subconsciously, or perhaps very consciously, weighs the expected benefits of the crime against the expected costs and risks.
Okay, so the text lists the actual variables in Becker's equation. Let's walk through this as if we are modeling someone deciding whether or not to commit, say, a specialized white-collar crime, like insider trading.
That's a perfect example.
The equation starts with Y, which is the time spent in criminal activity.
Right.
And that Y is a function of several independent variables. First, the wage of crime. So for insider trading, that's the massive illegal profit.
Correct.
Second, the legal wage. What could this person be making if they just worked their finance job legally?
Right. So the legal wage represents the opportunity cost. Every hour spent plotting the insider trade is an hour not spent earning a legitimate bonus.
Makes sense. Third, we have other income not from crime or work, like maybe they have a trust fund or a wealthy spouse.
Exactly. Baseline wealth changes the risk profile.
But then we get into the variables that Gicker used to quantify the risk, the cost side of the utility function. Variable 4 is the probability of getting caught.
Right.
Variable 5 is the probability of actually being convicted if you are caught.
Yeah.
And variable 6 is the expected sentence if you are convicted.
Okay, stop there for a moment because this is where the translation from theory to math gets truly fascinating.
Oh, how so?
Well, in Becker's theoretical model, we don't necessarily need to know the exact neural pathways of the criminal. We don't need the precise psychological formula.
We don't.
No, because the economic theory allows us to predict the direction of the effect.
Ah, the direction.
Exactly. If the probability of being caught goes up, say the SEC implements a new highly aggressive tracking software, the mathematical theory predicts the time invested in insider trading, our A variable will go down.
Because the expected cost of the utility function just spiked?
Exactly. And conversely, if the legal wage goes up, like if legitimate finance jobs start paying significantly higher bonuses across the board, the model predicts crime should go down.
Because the opportunity cost of risking it all is suddenly much steeper.
Exactly. You stand to lose too much guaranteed legal money.
And the final variable the text mentions is age, which factors into risk tolerance and time horizons. But here's the problem, and this is where I start struggling with the sheer ambition of econometrics.
What's the struggle?
Well, it's an elegant equation. Y equals a function of legal wage, illegal wage, probability of arrest, probability of conviction, expected sentence, and age. But how on earth do you actually put numbers to that?
Oh, yeah.
I mean, you can't survey people and say, excuse me, exactly how many hours did you spend committing crimes last week? And what was your perceived percentage chance of getting caught? They will lie, or they simply don't know.
You have hit on the exact boundary line between an economic model and an econometric model.
Okay, what's the difference?
The economic model is the theoretical skeleton. It's Becker sitting in his office mapping out rational behavior. But to do empirical analysis, we have to map that skeleton onto the real observable world.
And the real world is infinitely messy.
Exactly. We cannot measure the exact wage of a crime for a specific person. We rarely know a person's perceived probability of arrest.
So the model is broken before we even start?
Not broken, but incomplete. To make the model mathematically viable in the real world, the text introduces what is arguably the single most critical concept in all of econometrics.
Okay, what is it?
The error term. It is represented by the letter U. Sometimes it's called the disturbance term.
Okay, let's talk about us. Because in my head, I've always pictured the error term as basically a giant cosmic junk drawer.
A junk drawer.
Yeah, it's the place where econometricians sweep all the stuff they can't measure, all the messy human reality, just so the equation balances out. Is that fair?
It's a good starting point, but calling it a junk drawer makes it sound passive, like things just sit there harmlessly.
don't.
No, the error term is highly active, and it is actively trying to sabotage your analysis.
Wait, actively sabotaging how?
Let's look at example 1.2 from the text to see why. This is a simpler, more intuitive model, the job training program.
Right. The text says we don't always need a Nobel Prize-winning theory. Sometimes basic intuition gives us the skeleton.
Exactly.
So if we want to know how a training program affects a worker's productivity, which we measure by their hourly wage, the intuition gives us a simple equation. Wage is a function of education, experience, and training.
Precisely. We intuitively know that someone with more education and more experience generally commands a higher wage.
Right. That's just common sense.
But let's look at that equation through the lens of the real world. Imagine two workers. They both have exactly 12 years of education. They both have exactly 5 years of work experience. They both completed the exact same 20-week computer training program.
Okay, so according to the strict variables of our equation, they should be making the exact same hourly wage to the penny.
But we know for a fact they won't. One might be making $25 an hour, the other $32 an hour. Why? What accounts for the $7 difference?
The things in the junk drawer, the U term.
Exactly. The equation is fundamentally incomplete. In this wage model, the text explicitly states that U contains innate abilities, motivation, work ethic.
Oh, wow.
It contains the quality of the education they receive, not just the sheer number of years. It contains their family background, their networking connections, their interpersonal skills.
It contains a million microscopic factors that influence a salary, but that we cannot reliably capture in a spreadsheet.
Precisely. And if we go back to Becker's crime model, the text says the error term contains a person's moral customs.
Right, because you cannot quantify a person's internal moral compass or their threshold for guilt.
Exactly. It contains family background again. It even contains pure measurement errors. Like if the police department's statistics on how many people get arrested in a given year are just procedurally wrong.
Oh, so literally just bad data entry.
Yes, that mathematical error gets shoved into it as well.
Which brings us to the central crisis of econometrics. We have this error term, this U, and it is bulging with incredibly powerful, unobservable forces. What do we do with it?
Because we absolutely cannot ignore it.
Right. The text makes it very clear how we treat this error term, how we mathematically manage the things hiding in the junk drawer, is the defining component of any econometric analysis.
It really is.
Why is it a crisis, though? I mean, if we know we can't measure a person's innate ability, why can't we just accept that our wage prediction will be a little bit noisy?
Because it's not just noise.
Why can't we just say, well, the math is mostly right, plus or minus a few bucks because of the junk drawer?
Because the things in the junk drawer don't just add random noise. They systematically distort the variables you are measuring.
I'm not sure I follow.
Okay, imagine if innate ability, which is hiding unmeasured in Jun, is highly correlated with years of education, which is the variable you are measuring.
Okay, I see.
The highly able, highly motivated people are the ones who chose to stay in school for a master's degree. So if you run a simple regression to find the effect of education on wages, the math cannot distinguish between the pure effect of the degree and the hidden effect of the person's innate motivation.
Oh, wow. So the math will look at the high wage and give all the credit to the master's degree, completely ignoring that the person's unstoppable work ethic, which was hidden in the junk drawer, was actually doing half the heavy lifting.
Precisely. The unobservable variable in the URL reaches out and actively contaminates the observable variable. Your estimation of the value of education becomes completely biased. It is mathematically wrong.
That is terrifying for an analyst.
It is. This is why econometricians spend their entire careers obsessing over the structure of it.
We are going to dive incredibly deep into how they solve that contamination problem later. But before we can even run the math, before we can interrogate the junk drawer, we need to know what kind of playing field we are on.
Yes, the data structures.
Right, because an equation is useless without data, and the text breaks down the data universe into very specific structures. It turns out you can't just throw numbers into a computer.
Not at all. The actual shape of the data dictates the mathematical tools you are allowed to use.
So architecture of the data is destiny in econometrics. The text categorizes non-experimental data into a few fundamental structures, starting with cross-sectional data.
Let's start there. Cross-sectional data.
Okay, cross-sectional data. The text defines this as a sample of individuals, households, firms, cities, states, or countries taken at a given point in time.
Yes.
It gives table 1.1 as the classic example. This is a data set from the year 1976. It features 526 individual workers.
A very famous data set in econometrics, actually.
Really? Well, for every single worker, it lists their wage, their years of education, their years of experience, a 0 or a 1 for whether they are female, and a 0 or a 1 for whether they are married.
The defining characteristic of a cross-section is that it is a snapshot. Time is frozen. You're looking at a slice of the population in a singular moment.
And the text points out some very specific mathematical quirks about this snapshot. First, the ordering of the data is completely irrelevant.
Completely irrelevant.
Like, worker number 1 could be swapped with worker number 500 in the spreadsheet, and it makes absolutely zero difference to the underlying econometric math.
Because there is no chronological linkage between the units. They are distinct entities captured simultaneously. But more importantly, the mathematical validity of a cross-sectional analysis relies almost entirely on the assumption of random sampling.
Why is random sampling the life or death assumption here?
Because we want to make inferences about a massive population, say, the entire U.S. labor force. But we only have the budget to measure a snapshot of 526 people.
Right.
If we randomly select those 526 workers, the laws of probability ensure that our small snapshot accurately reflects the demographics, the wage distribution, and the educational variance of the whole country.
So the sample is representative.
Exactly.
Yeah.
But the text notes that in the real world, true random sampling is notoriously difficult to achieve, and sometimes it gets severely violated.
Yeah, I imagine people don't always want to cooperate with surveys.
It happens constantly. Suppose you are trying to study the relationship between family wealth and savings habits. You send out thousands of surveys. Who is most likely to throw that survey straight into the trash?
Extremely wealthy families.
Exactly. They value their privacy, or they simply don't have the time to fill out a questionnaire for a university researcher.
So if the billionaires all opt out, your snapshot is fundamentally skewed.
Your sample is no longer random, it is truncated at the top end. If you run a regression on that skewed cross-section, your conclusions about national wealth dynamics will be entirely false because the data structure itself was compromised from the start.
The text gives another example of a cross-section in Table 1.2, GDP growth across different countries. Again, a frozen snapshot in time, comparing Japan's growth to Germany's growth in a specific year.
Another classic cross-section.
But then the text flips the script and introduces the second major data structure, time series data. This isn't a snapshot. It's observations of variables over time. Daily stock prices, weekly money supply, annual gross domestic product.
Right. If cross-sectional data is a photograph of a crowd, time series data is a movie focused on a single subject. You're watching how one specific entity evolves chronologically.
Right. But here's where I need you to clarify something, because the text makes a very big deal out of this.
Okay. What is it?
If time series is just watching one thing over time, why is it mathematically so much harder to analyze than a cross-section of 1,000 people? The text implies that time series data causes massive statistical headaches.
It causes headaches because time series data aggressively violates a core assumption of basic statistics, the assumption of independence.
Let's break that down. What does independence mean in this context?
Go back to our random cross-sectional snapshot of the 526 workers. If you randomly select person A and person B from completely different parts of the country, person A's hourly wage has absolutely no impact on person B's hourly wage.
Right.
Knowing person A's salary gives you zero predictive power regarding person B's salary. The observations are independent.
Okay, that makes total sense.
But in a time series movie, economic observations are almost never independent from their own history. The past actively dictates the future.
Wait, how?
Let's look at the example of gross domestic product. If you know the U.S. GDP for the third quarter of the year, you have an incredibly strong indicator of what the GDP will be in the fourth quarter.
Oh, because an economy doesn't just randomly reset to zero every 3 months.
Exactly. The data is heavily correlated with itself. Econometricians call this autocorrelation or serial correlation.
So the data is basically echoing itself over time.
Echoing itself, exactly. We also call it persistence or a lag structure. A shock to the economy today, say a sudden spike in oil prices, doesn't just affect today's data.
It lingers.
Yes, its effects reverberate or lag into next month's data, and the month after that, slowly decaying over time. You don't have trailing echoes in a random cross-sectional snapshot. You only have them in time series.
And the text points out other time-specific headaches too, like periodicity. The frequency of the data matters. Daily data behaves mathematically differently than annual data. And then there's seasonality.
Seasonality is a perfect example of a predictable time series distortion. The text mentions housing construction.
Oh, right.
If you track monthly housing starts, the graph will predictably plummet every single December, January, and February. Not because the underlying economy is crashing, but simply because the ground is frozen and you can't pour a concrete foundation in a blizzard.
So if you are an econometrician trying to see if a new interest rate policy is boosting the housing market, and you look at data from November to January, it looks like the policy completely failed.
Exactly. Unless you mathematically account for the changing of the seasons. You have to build specific parameters into your model to filter out the winter drop, isolating the true economic trend from the mere passage of the calendar year.
That sounds incredibly complicated.
It is. And furthermore, because chronological order is the entire point of a time series, you cannot just shuffle the data like a deck of cards the way we said you could with the 526 workers. Observation 1, January, must mathematically precede Observation 2, February. The order is rigidly fixed.
The text uses Table 1.3 to illustrate time series data, and this is an interesting one. It tracks the minimum wage and the unemployment rate in Puerto Rico, starting from the year 1950 and going forward chronologically.
A very classic macroeconomic time series.
And I want to pause here for a second and speak directly to you, the listener. The source text uses this historical data from Puerto Rico strictly as a structural demonstration. The text eventually discusses the complex econometric process of examining the relationship between minimum wage increases and unemployment levels over time.
Right.
It is a highly debated topic in economics, but the text is using it to show how a time series is analyzed, not to draw a definitive, universal political conclusion about minimum wage laws. And neither are we. We are looking exclusively at the architecture of the data and the mathematical tools required to analyze it.
That is a crucial distinction. Econometrics provides the mathematical framework to interrogate the data. But as analysts, we must rigorously separate the statistical mechanics of the time series from the political or ideological discourse that surrounds the variables being measured.
Right.
The math doesn't have a political party.
Exactly. Okay, so we have cross-sectional snapshots. and we have time series movies. But what if we want the best of both worlds? What if we want a movie of the entire crowd?
Now we get to the really good stuff.
This brings us to section 4 of the text, pooled cross-sections and panel data. When I was reading this, it felt like unlocking the next level of econometrics.
It absolutely is.
Yeah.
When you start combining the spatial breadth of cross-sectional data with the chronological depth of time series data, you unlock analytical superpowers. You suddenly have the tools to tackle that insidious error term, the U.
Let's start with the first combination the text offers, pooled cross-sections. This is when you combine two entirely different cross-sectional surveys taken in different years. The textbook example involves housing prices. Imagine taking a random survey of 250 houses sold in the year 1993. You record their prices, square footage, number of bedrooms.
Okay.
Then, the city implements a massive property tax reduction in 1994. To see what happened, you take a brand new random survey of 270 houses sold in the year 1995. You pool the 1993 dataset and the 1995 dataset together into one giant spreadsheet.
By pooling independent cross-sections from different time periods, you achieve two major analytical goals. First, you simply increase your overall sample size from roughly 250 to over 500, which gives your statistical estimations more mathematical precision.
Because more data points generally mean tighter confidence intervals, right?
Exactly. Second, and much more importantly, you can analyze the effect of a specific historical event, the 1994 tax cut, by comparing the pre-policy snapshot to the post-policy snapshot.
But wait, the text is very careful to distinguish pooled cross-sections from the final data structure, which is panel data or longitudinal data.
Yes, very careful.
The example it gives for panel data is Table 1.5. This table shows crime statistics, population size, and the number of police officers for 150 specific cities. And it shows the data for those 150 cities in the year 1986, and then again for those same 150 cities in 1990.
Okay, I see where you go.
Now, I have to play devil's advocate here. To me, the 1993 and 1995 housing price example and the 1986 and 1990 city crime example sound mechanically identical. You have data from an early year, an event happens in the middle, and you have data from a later year. Why does the text make such a massive, fundamental distinction between pooled data and panel data?
It is the most important distinction in empirical microeconomics. The difference isn't in the timing. The difference is in the identity of the subjects.
The identity.
Think deeply about the pooled housing example.
Yeah.
The 250 houses that happened to be sold in 1993 are almost certainly completely different physical houses than the 270 houses sold in 1995.
Oh, right.
You took a snapshot of the housing market at two different times, but the individual units making up the snapshot have entirely changed.
Okay, I see. I'm looking at the crowd in 1993, and then I'm looking at a completely different crowd in 1995.
Exactly. But in the panel data, the longitudinal data, you are tracking the exact same 150 cities in 1986 and 1990. City number 1 in 1986 is the exact same geographical, cultural, and political entity as city number 1 in 1990. You are following the identical cross-sectional units over time.
Okay, that makes logical sense. But why is it so incredibly mathematically valuable?
It's game-changing.
The text openly admits that panel data is vastly more difficult and expensive to collect. You have to track down the exact same people or firms years later. But it hints that panel data is the ultimate weapon in econometrics. Why?
Because it is the ultimate weapon against our old nemesis, the junk drawer. The error term U.
Wait, really? How does tracking the same city kill the error term?
Let's walk through the mathematical logic verbally. We are trying to figure out if hiring more police reduces crime. Remember, the junk drawer contains all the unobservable factors that skew our data.
Right, the stuff we can't measure.
So if we only have a single 1986 snapshot of a city, we can see its crime rate and its police force. But we cannot see its unobservable, deeply ingrained cultural quirks.
Like what?
We can't quantify its unique historical geography or the deeply entrenched institutional norms of its local court system. All of that unobservable fixed culture is hiding in found, secretly influencing the crime rate and biasing our math.
Because maybe a city with a historically tough working-class culture naturally has a slightly higher baseline of petty crime, regardless of how many cops are on the street, and we can't measure tough culture in a spreadsheet.
Exactly. Now let's build the equation for City A in 1990. Crime in 1990 equals the effect of the police in 1990 plus whatever temporary economic shocks happened in 1990 plus the fixed unobservable culture.
Okay, crime 90 equals police 90 plus shocks 90 plus fixed culture. Got it.
Now write the exact same equation for City A in 1986. Crime 86 equals police 86 plus temporary shocks in 86 plus the fixed unobservable culture.
Wait, the fixed culture is exactly the same in both equations. Because it's a deeply ingrained historical norm, it hasn't fundamentally changed in 4 years. It's a constant.
It is a constant. So what happens if we take the 1990 equation and mathematically subtract the 1986 equation from it?
You difference them. Crime 90 minus crime 86 gives you the change in crime. Police 90 minus police 86 gives you the change in cops. But fixed culture minus fixed culture, well, that just equals zero.
It equals zero. It drops out of the equation entirely.
Oh, wow.
By tracking the exact same entity over time, you can mathematically difference out or subtract away all the unobservable time-constant variables hiding in the junk drawer.
That is incredible.
You have used the structure of panel data to neutralize the most stubborn biasing elements of the error term. You don't even need to know what the unobservable culture is. You just need to know it hasn't changed and the math deletes it.
That is genuinely brilliant. We bypassed the thing we couldn't measure by just subtracting it from itself.
Sure.
And this obsession with deleting the error term, with neutralizing the unobservables, leads us directly to the core philosophy of the entire textbook, the holy grail of econometrics, causality and the concept of ceteris paribus.
This is where we separate the serious empirical scientists from the people who just play with spreadsheets.
What do you mean?
Well, finding a statistical relationship, a simple correlation between two variables is easy. Anyone with basic software can do it. But finding a correlation is not enough. Economists do not just want to know if A and B move together. They want to prove a causal effect.
Right.
They want to prove that changing variable A literally caused the change in variable B.
And the text says this entire quest for causality relies on one Latin phrase, ceteris paribus, which translates to holding all other relevant factors constant.
It is the foundational requirement for isolating a causal mechanism. Let's say you want to know how increasing the price of a specific car affects consumer demand for that car.
Yeah.
To find the true, pure causal effect of the price increase, you have to assume that absolutely everything else in the universe remains exactly the same. Ceteris paribus.
So consumer income hasn't changed, the price of rival cars hasn't changed, the price of gasoline hasn't changed?
Correct. Because if the price of the car goes up, but simultaneously the entire country enters an economic boom and everyone's income triples, demand for the car might actually increase, despite the higher price.
Oh, I see.
If you don't hold income constant, if you don't achieve ceteris paribus, your data will falsely tell you that raising prices increases demand. Your analysis is fundamentally confounded by the moving variables.
The text gives two distinct examples to illustrate just how difficult achieving ceteris paribus is in the real world. I want to look at the fertilizer versus education dilemma.
That's a great comparison.
Let's start with example 1.3, testing the causal effect of fertilizer on soybean yield. If an agricultural researcher wants to know if a new chemical fertilizer causes beans to grow bigger, they don't have to rely on messy observational data. They can run a literal, physical experiment.
Yes. The researcher can take a massive varied field, divide it into equal grid plots, and use a random number generator to assign different amounts of fertilizer to each plot.
Okay.
Because the assignment is purely random, the amount of fertilizer applied is completely independent of the underlying quality of the soil.
Meaning the computer doesn't care if a specific plot has naturally rich, loamy soil or terrible, rocky soil. The fertilizer assignment is completely blind.
Exactly.
Some excellent soil gets 0 fertilizer, some terrible soil gets 10 pounds of it. It is perfectly randomized.
And that randomization is the key to the kingdom. By randomly distributing the treatment, the researcher effectively holds all the other unobservable factors like soil quality, microdrainage, slight elevation differences, constant on average across the different groups.
So they artificially achieve ceteris paribus.
Yes. When harvest time comes, any statistically significant difference in soybean yield between the groups can be confidently, mathematically attributed entirely to the causal effect of the fertilizer.
The random assignment does all the heavy lifting. But then, look at example 1.4, measuring the return on education.
A much messier problem.
We want to know the causal effect of completing one more year of schooling on a person's future hourly wage. The text points out that we cannot run this like the fertilizer experiment. We cannot act as a giant authoritarian social planner.
As we discussed earlier, we cannot take a random sample of 1,000 10-year-olds and say, you 500 are legally forbidden from attending school past the 8th grade, and you other 500 are legally mandated to complete a PhD regardless of your grades or desires.
Right. So we are stuck. We can't experiment. So we have to use observational data. We have to look out at the world, find people who already chose their education levels, look at their current wages, and try to run the math.
Yes, but the text warns us about a massive structural trap that ruins this observational data.
Self-selection.
Self-selection, how does that work? Self-selection is the Achilles heel of almost all observational microeconomics. In the real world, people choose their education levels. The treatment is not randomly assigned. It is actively selected by the subject.
Okay.
And here's the fatal flaw. The individuals who choose to pursue higher education likely possess entirely different underlying characteristics than those who drop out early.
They aren't blank slates. The text specifically mentions innate ability and experience as the confounding variables. Let's break that down.
Sure.
A person with high innate intellectual ability or a relentless natural work ethic might find high school and college significantly easier and more rewarding than someone who struggles in a traditional academic setting.
Exactly.
Therefore, the high ability person is far more likely to self-select into college.
And conversely, people who stay in school for a master's degree generally enter the full-time labor force 4 or 5 years later than someone who went straight to work after high school.
Right.
So at age 25, the high school grad has significantly more real-world work experience than the fresh college grad.
So the variable of education is deeply, invisibly entangled with the unobservable variables of innate ability and experience.
Precisely. They're tangled together in the data. If we just run a naive regression comparing the wages of college grads to high school grads using observational data, we aren't just measuring the isolated effect of the diploma.
What are we measuring then?
We are measuring the effect of the diploma plus the hidden wage boost from their higher innate ability, minus the hidden wage penalty of their lower work experience. We have completely failed to hold those other factors constant. We have failed to achieve ceteris paribus.
Let me see if I can bring this together with an analogy based on the text.
Go for it.
Running a simple regression on observational data of smart, highly motivated people choosing to get more education is exactly like a farmer deciding to test a new fertilizer. But instead of randomizing it, he secretly chooses to dump all the new fertilizer exclusively on the plots of land that he already knows possess the absolute highest natural soil quality.
Yes, the treatment is actively correlated with the unobserved advantage.
If he does that, the end results at harvest are going to be completely skewed. He's going to look at the massive soybean yield on those specific plots, point to the data, and say, wow, the mathematics prove this fertilizer is pure magic. It increased yields by 400%.
Right.
But he's blind to the fact that the rich soil was naturally generating 300% of that yield all on its own before the fertilizer even touched it.
That is exactly the dynamic. In econometrics, the farmer's secret knowledge about the soil quality is the unobservable variable lurking in the error term.
The junk drawer strikes again.
Exactly. If the application of the variable we are trying to study, whether that is fertilizer or a college degree or a job training program, is correlated with the unobserved variables in the junk drawer, like soil quality or innate ability, our mathematical estimation of the causal effect will be wildly exaggerated, or sometimes completely backwards. Economists refer to this as spurious correlation, driven by selection bias.
And this problem, this reality of variables being deeply, invisibly tangled together, isn't just an academic puzzle for a textbook. It has immediate, high-stakes consequences for how we evaluate massive, real-world policies.
It absolutely does.
Which brings us to the final major section of our deep dive, real-world policy traps. The text gives 3 prime examples of how these econometric tangles manifest in the real world and how they routinely trick policymakers, journalists, and voters.
These are the exact traps that generate those misleading, sensationalist headlines we see every day when people look at raw data without understanding the underlying econometric architecture.
Let's start with example 1.5, police and crime. This is a classic. The policy question is incredibly straightforward. Does adding 10 police officers to a city's force actively reduce the amount of crime in that city?
Seems like a simple math problem, doesn't it?
It does, but the text explicitly states that you cannot just look at observational cross-sectional data, compare city A to city B, and draw a causal conclusion. Why not?
Because of a deeply problematic phenomenon called simultaneous determination, which is a specific and severe form of endogeneity.
Simultaneous determination. Okay, what is that?
To understand it, you have to think about how a city actually operates in the real world. A city council does not randomly decide how many police officers to hire by rolling dice. The hiring decision is a direct reaction to the environment.
Oh.
If a city suddenly experiences a massive, terrifying crime wave, what is the mayor going to do?
Well, the mayor is going to panic, pass an emergency budget, and hire 50 new police officers immediately to show the voters they're doing something.
Exactly. High crime actively causes the hiring of more police. But simultaneously, the very purpose of hiring those police is to cause the crime rate to go down. The two variables, the size of the police force and the volume of crime, are locked in a feedback loop. They are determining each other simultaneously.
Okay, I see the loop, but how does that ruin the math if we just look at the data?
Imagine you take a cross-sectional snapshot of 100 cities today. You plot them on a graph. On one axis is the number of police per capita. On the other axis is the crime rate. Because of that feedback loop, the cities with the absolute highest crime rates are almost guaranteed to be the cities that have desperately hired the largest police forces.
Oh, so the raw data will show a strong positive correlation. Lots of cops equals lots of crime.
Yes. And if a naive data analyst or a journalist just runs a basic regression on that snapshot without understanding simultaneous determination, the math will objectively output a positive coefficient.
Oh, no.
The analyst will proudly publish a report concluding the data proves it. Hiring more police officers causes crime to increase.
That is mind-bending. The raw objective data can literally show you the exact mathematical opposite of the truth if you don't untangle the feedback loop.
The endogeneity completely hides the true causal effect. The reality might be that the large police force is actually suppressing the crime rate, bringing it down from the catastrophic level it would have reached without them.
Right.
But the simple correlation is blinded by the fact that this severe crime wave caused the cops to be there in the first place. Untangling simultaneous equations is one of the most advanced, difficult tasks in econometrics.
The text gives another example of a trap, which is example 1.6, the minimum wage. We want to know the causal effect of raising the minimum wage on the unemployment rate. We look at that time series data from Puerto Rico. But again, the text warns us that we can't just draw a straight line between the two variables.
Because, much like the police force, the minimum wage is not determined in a vacuum. It is deeply endogenous.
Let's define endogeneity here, because we've used the word a few times. Basically, it means the variable we are trying to study is being influenced by the exact same hidden forces that are influencing the outcome we are measuring. It's an internal tangle rather than an external independent force.
Precisely. A purely exogenous variable is like the randomized fertilizer. It falls from the sky, unaffected by the soil. An endogenous variable is generated from within the system itself. The minimum wage is highly endogenous. It is set by politicians, and politicians are highly reactive to the broader macroeconomic conditions.
Walk me through how that corrupts a time series analysis.
Consider the political reality. If the economy is booming, GDP is soaring, and unemployment is naturally incredibly low, politicians feel very comfortable passing legislation to raise the minimum wage.
Right, because the economic pie is expanding and businesses can absorb the cost.
Exactly. But if the country is plunging into a deep, painful recession and unemployment is skyrocketing, politicians will almost certainly freeze the minimum wage, terrified of putting extra burdens on struggling businesses.
So the historical level of the minimum wage is intimately, invisibly correlated with the overall unobservable health of the macroeconomy.
Exactly. And the health of the macroeconomy is the primary driver of the unemployment rate.
Ah, I see the tangle.
So if you look at the time series, you might see periods where the minimum wage went up, but unemployment stayed low. A naive analyst says, see, raising the minimum wage causes no unemployment.
But they are failing to achieve ceteris paribus.
They're failing to account for the fact that the underlying booming economy, the unobservable macroeconomic strength hiding in the error term, is what kept unemployment low, and it's what caused the politicians to raise the wage in the first place.
It's the farmer putting the fertilizer on the naturally rich soil all over again. You completely fail to isolate the isolated effect of the minimum wage because it's tangled up with the massive macroeconomic forces sloshing around in the junk drawer.
Which brings us to the third example from the text, example 1.7. This one is conceptually a bit different from evaluating a government policy, but it is equally important for understanding the scope of the discipline. It deals with testing the expectations hypothesis in financial economics.
Yeah, this example shifts us into the world of investment banking and U.S. Treasury bills. The underlying financial theory says that if a market is highly efficient and investors have access to all available information, the expected return on different investment strategies that cover the same time horizon should equalize. There shouldn't be a magical free lunch.
Because if one strategy reliably produced a higher risk-free return, every rational, utility-maximizing investor would immediately rush to exploit it, which would instantly drive the price up and eliminate the advantage.
The text compares two specific strategies. Strategy A, you buy a 3-month Treasury bill. It's straightforward. You buy it, hold it for 3 months, and you know exactly to the penny what your payout will be. There is zero uncertainty about the return.
Strategy B is more complex. You decide you want to invest for 3 months, but instead of buying the 3-month bill, you buy a 6-month Treasury bill. Your plan is to hold it for exactly 3 months and then sell it on the secondary market halfway through its lifespan.
And the text points out the crucial difference here, uncertainty. With strategy B, you know the exact price you paid for the 6-month bill today, but you have absolutely no idea what the secondary market price will be when you try to sell it in 3 months. If interest rates spike in the meantime, the value of your half-used T-bill will plummet. It's risky.
However, the expectations hypothesis dictates that accounting for risk premiums, the expected mathematical return of strategy B must equal the guaranteed return of strategy A. If it didn't, the market would be fundamentally irrational.
So why is this an econometrics problem? We aren't trying to figure out if cops cause crime.
Because econometrics isn't just about finding causal policy effects. It is also the primary mechanism for testing if these elegant ivory tower economic theories actually hold true in the wild, messy reality of the data.
Oh, I see.
An econometrician will take decades of highly granular time series data on T-bill yields, build a model that accounts for the risk premiums and the lag structures we discussed earlier, and rigorously test if the mathematical relationship perfectly holds. If the econometric analysis repeatedly proves the returns do not equalize, then the entire theoretical foundation of the expectations hypothesis has to be torn down and rewritten.
Okay, we have covered a massive amount of ground, and honestly, seeing all these traps, the simultaneous determination, the self-selection bias, the endogenous political variables, it's a little overwhelming.
It is a lot to take in.
If everything in the real world is simultaneously determined or actively self-selected or hopelessly entangled with massive, unobservable cultural and economic factors hiding in the error term, well, how do economists ever actually find the truth? How do they ever definitively prove causality? Are we just doomed to be tricked by spurious correlations forever?
We are not doomed, and that is the fundamental optimism of the textbook. The text promises that while the data is messy, the mathematics are powerful.
Powerful enough to untangle all that.
Yes. By carefully, rigorously applying advanced econometric methods to this observational data, we can actually mathematically simulate the conditions of a randomized ceteris paribus experiment.
You can build the sterile laboratory inside the computer.
Exactly. Through highly sophisticated techniques, things like multiple regression analysis, which mathematically controls for observable factors, or utilizing panel data to perfectly difference out those deeply ingrained, unobservable, fixed traits. Econometricians can artificially hold the metaphorical soil quality or the innate ability constant, even when they have absolutely no physical control over it in the real world. They use the mathematical architecture to meticulously clean out the junk drawer.
They shrink the U until only the pure causal relationship is left standing.
That is the goal.
So what does this all mean for you, the listener? Why should you care about the difference between a time series and a cross-section, or the mechanics of an error term? It matters because it completely changes your diagnostic toolkit for reality.
It changes how you consume every piece of information presented to you as data-driven.
Exactly. The next time you are sitting in a board meeting, or the next time you read a bold, viral news headline claiming, "New study proves policy X reduced crime by 20%, or eating blueberries causes longer lifespans, your reflex should no longer be blind acceptance.
Right.
Your very first question should be, wait a minute, did they actually manage to mathematically simulate a ceteris paribus experiment? Did they rigorously control for what was hiding in the junk drawer? Or did they just take a cross-sectional snapshot of a tangled, endogenous mess of self-selection and simultaneous determination and call it a day?
You stop accepting simple, naive correlations at face value, and you start demanding to see the causal architecture beneath the claim. You become immune to bad statistics.
Let's do a quick structural summary of the journey we just took through Chapter 1 of Wooldridge. We started by defining the distinct mission of econometrics, the science of extracting truth from non-experimental observational data, operating like an astronomer rather than a chemist. We learned how to translate theoretical intuition into empirical equations, acknowledging that human behavior can be mapped mathematically using utility maximization, as perfectly illustrated by Becker's cold, calculating model of the criminal mind.
We then explored the absolute necessity and the profound danger of the error term, U, the mathematical repository for all the unobservable forces that actively attempt to bias our analysis.
We surveyed the shape of the data universe, realizing that the structure dictates the math. We looked at cross-sectional snapshots relying on random sampling, the mathematical headaches of time series movies with their persistent autocorrelations and lag structures, and finally, the golden key of panel data, tracking the exact same entities over time to mathematically subtract away the hidden, fixed quirks of culture and geography.
And all of that methodological groundwork led us to the ultimate unforgiving quest of the discipline, achieving ceteris paribus, the necessity of holding all else constant to prove pure causality, forcing us to navigate the treacherous traps of self-selection, endogeneity, and simultaneous determination that skew our understanding of critical issues like education returns, police effectiveness, and macroeconomic wage policies.
It is a massive, incredibly powerful conceptual toolkit. But before we wrap up this deep dive, I want to leave you, the listener, with a final mind-bending thought to mull over, one that is directly inspired by the theoretical limits of the text we just explored.
Oh, I like where this is going.
We've spent the entire hour talking about how econometrics is this constant, heroic mathematical battle to quantify and neutralize the unobservable factors hiding in the error term. Things like innate ability, family background, risk tolerance, and moral customs.
Yes, the entire discipline is essentially a perpetual struggle to systematically shrink the influence of the junk drawer.
Right. So follow that logic to its absolute futuristic conclusion. What happens if the econometricians eventually win? What happens if technology, generations from now, becomes completely omniscient?
Omniscient.
Yeah. If our data collection methods, our biometric sensors, our total digital footprints, and our quantum computing power become so absolute, so flawlessly total, that the error term essentially drops to absolute zero.
Wow.
If, 100 years from now, a super econometrician can mathematically account for every single invisible factor, every microscopic childhood experience, every subtle genetic predisposition, every firing synapse that drives a human choice, if we can finally perfectly predict human behavior by mathematically holding literally everything in the universe constant, does human free will simply cease to exist?
That is quite the question.
Does our entire lived experience, our feeling of making a choice, simply become just another perfectly known parameter, perfectly solved in a massive, inescapable econometric equation? Think about that. Until next time.